Alice and Bob are playing a stone game where the stones are laid out in a row and each stone is worth some number of points. Taking turns, with Alice going first, each player grabs either 1, 2 or 3 stones from whatever's left at the front of the row, adding up the values of the stones they take as their score. Beginner level, let's start with a little trap. Picture 4 piles of stones in a row, 1, 2, 3, 7. Say Alice's plan is grab as many stones as I can, as fast as I can, so she scoops up the first 3 piles for 1 plus 2 plus 3, 6 points. Sounds smart, right? But now there's only one pile left, the 7, and it's Bob's turn. He takes it and wins with more points than Alice. So the lesson here, before we write a single line of code is, taking more stones does not mean winning more code is, taking more stones does not mean winning more points. Pick that in your back pause 2 plus 3, 6 points. Here is the full setup. We're given a list of stone values. Sometimes the value is even negative, meaning that pile actually hurts your score. On each turn, whoever's playing must take 1, 2 or 3 stones, but only from the front of the row. You can never reach in and grab from the middle. Alice always goes first, and optimally just means every player always picks the smartest move available, never a careless one. At the end, we compare total scores and report who won. Alice, Bob or a tie. One more thing, the row can be up to 50,000 stones long, so whatever we build has to be fast, not just correct. Here's a picture that might make this click. Imagine 2 kids taking turns pulling coins out of one end of a jar, and both of them are trying their absolute hardest to end up with more money than the other. That's really all this problem is. And it's not just this one problem. A whole category of coding interview questions is built on exactly this shape. 2 players, 1 row, take turns. So the trick we're about to learn isn't a one-off hack. It's a pattern you'll recognize again. Let's test our understanding on a small row. 1, 2, 3, 6. Genuinely, pause the video, grab a pen, and try to play this out by hand as both Alice and Bob. If you do, you'll find something surprising. No matter what Alice opens with, she can't force a win. The very best she can guarantee, if Bob also plays perfectly, is a tie. Hold on to that result. We'll circle back to it soon, and it'll make a lot more sense once we've built our tool. Before we write code, let's make sure 4 small Python pieces feel familiar, because we are about to lean on all of them. First, a list. Think of it as a shelf with one labeled slot for each stone. DP3 means the slot for stone number 3. Second, range can count backward. Range 3, DP2 1, DP2 D2 1, DP decays, U3 D2 1, DPC, like reading a recipe steps from the last one back to the first. Third, float infees is just a number, so low that literally any real number beats it. Useful as a starting point when you're about to search for the biggest option and don't have one yet. And fourth, maxia, B simply returns whichever of A or B is bigger, no different from comparing 2 prices. The most natural first idea is to literally simulate the game. Try taking 1 stone, then imagine both players playing perfectly from there. Then rewind and try taking 2 stones instead. Then rewind again and try 3. I actually wrote this exact approach my first time through this problem, keeping a separate running score for Alice and a separate one for Bob. It worked, but it turned into a tangled mess to keep straight. And there's a bigger problem, every single stone branches into 3 possible futures. So the number of possibilities explodes. Fine for 4 stones, hopeless for 50,000. We need a way to boil this whole tangled decision down to just 1 stone. Then imagine both these custom. Which number? Keep watching. This is the one idea the entire solution rests on, so let's slow way down. Instead of tracking Alice has this many points and Bob has this many points as 2 separate numbers, we track just one number, the difference between the current player's score and the other player's score. From this point in the row onward, assuming both play their best. We call that DPI starting from stone I. How far ahead can whoever's turn it is end up? Here's the clever part. We never say the word Alice or Bob inside this number. Whoever's turn it happens to be is just the current player and their opponent is the other player. That means the exact same rule works whether it's Alice's turn or Bob's turn. We don't need 2 sets of logic, just one. If DPI comes out positive, the player moving at position I can force themselves ahead. That's the whole trick. So how do we actually compute DPI? The current player has 3 choices. Take 1 stone, take 2 or take 3 and they'll pick whichever choice works out best for them. For each choice, add up the stone values they just grabbed. That's their gain this turn. Then subtract DP at the spot right after what they took. Why subtract? Because once they hand over the rest of the row, the opponent becomes the current players, starting for that smaller row, and DP for that smaller row, and DP for that smaller row is the opponent's best possible lead over us. So their gain is our loss, hence the minus sign. Notice this means DPI depends on DP values further to the right. At IPI, DPI depends on DPI at after what they took. Well, it's true. IPI 3, values we haven't computed yet if we go left to right. So we have no choice but to fill this table. Let's zoom into one single turn so this really sticks. Say the current player decides to take 2 stones from the front. Both of those stone values get added straight into their score for this turn. That part's simple addition. But what happens to the rest of the rack passes to the other side. It doesn't vanish, it becomes the opponent's row now, starting fresh from wherever we stopped. The opponent gets to play that remaining row perfectly, just like we would, and whatever lead they build for themselves counts against us. Which is exactly why we subtracted. One decision and just like that, control of the gap passes. Now let's turn that idea into code, line by line. DPH row 6 in +1 makes a list with 1 slot for every stone plus 1 extra slot at the very end. That extra slot DPN represents an empty row, nobody left to play, and its gap is naturally 0. The outer loop for I and range in rows X in rows 1 to ascend rows in rows 1 is that backward counting we talked about earlier. It starts at the last stone and walks all the way down to the first, because DPH needs the later slots already filled in. Inside, best starts at -infinity. Remember, that just means nothing beats this yet. Intake starts at 0, building up as we add one more stone each pass. Once the whole DP list is filled in, the answer is sitting right there at DP0 loss. Since Alice moves first, DP0 is exactly her best possible lead over Bob across the entire row. If that number is positive, Alice comes out ahead, so she wins. If it's negative, Bob comes out ahead. And if it lands exactly on 0, neither player could get ahead of the other, so it's a tie. That one line just reads the sign of a number and turns it into a name. Here's everything we just built, together on one screen. Make the DP list, fill it backward one score, gap at a time, then read the sign of DP0 to name the winner. Nothing in this block should feel unfamiliar anymore. We walked through every single line already. Let's plug in real numbers, so this isn't abstract anymore. Take our row 1, 2, 3, 7 and suppose we are figuring out DP at index 1 and we are testing the choice. Take 2 stones. Those 2 stones are the values at index 1 and index 2, which are 2 and 3. So take starts at 2, then we add 3, giving us take stones 2. And taking through stones 2 and Bex taking 2 stones, K starts at 0. So K stones is take minus DPI plus K's plus 1, which here is DP1 means 2 stones, is take minus DPY plus K's plus 1 in DP3. This one slot past the last stone we grabbed, exactly where the opponent's turn would begin. So this one candidate is 5 DP3. We do this for taking 1 stone and taking 3 stones too. And best. Now let's run the full algorithm on the row from the very start of this video, 1, 2, 3, 7, and watch every single slot get filled. We start at the back, DP4S is the empty row slot, so it's 0. Working backward, DP3 to 7 only 1 stone left, so you just take it. DP2 to 7 and SS, DP2 decision TP2 decision to S, 1 to decision tuition. 2 decision to S, 1, that negative number means Alice, who always moves first, so DP just risen to S and decision to S is 1 point behind Bob when both play their absolute best, so the function returns Bob. And notice that's exactly what we predicted by hand at the very beginning of the video when greedy grabbing backfired on Alice. The DP tables numbers instead of intuition. Your turn. Euro 1, 2, 3, -9. Same rules as before, both players play the smartest possible game, Alice goes first. Genuinely pause the video right now and think it through. Does Alice want that last pile or does she want to stay far away from it? Once you've got a guess, press play and we'll check it together. Here's the answer. Alice's smartest move is to grab all 3 good stones right away. 1 plus 2 plus 3, 6 points for her, leaving Bob with nothing left but the -9, which actually subtracts from his score. Run this through our DP code and DP0 comes out to +15, a huge lead for Alice. Positive gap means Alice wins. Same score gap means Alice wins. Same score, gap trick, brand new row, and it still just works. That's the whole point of building a general rule instead of memorizing one example. 3 traps to watch for. First, tracking Alice's score and Bob's score as 2 separate arrays. That's exactly what I did the first time I solved this, and it turns a clean one array solution into a confusing mess. Second, making the DP list only n slots long and forgetting the extra slot for empty rows at index n. Without it, the very first backward step has nothing to subtract and the whole calculation breaks. Third, and this is the one from our opening example, assuming grabbing more stones is automatically better. It isn't. As soon as a pile is huge or negative, greedy grabbing can actively hurt you. Exactly like Alice losing to Bob's slot for empty rows at index n. Quick side note, before we wrap up, you could also write the same idea top down, meaning you write a recursive function that calls itself and saves each answer so it's never recomputed twice. That version can actually read a bit closer to the plain English rules of the game. But recursion in Python means the computer stacks up one function call per step, and with up to 50,000 stones that risks hitting Python's recursion limit for no real benefit. Our backward loop or bottom-up version never has that problem. It's one straightforward pass, so I'd always ship that version. The chart shows why naive simulation without any saving of results. Branches 3 ways at every single stone and explodes a function that calls exponentially, while our DP does exactly one clean pass through the row. Let's sanity check the edge cases. The situations that trip up code that only sort of works. A row with just one stone, Alice simply takes it, nothing to strategize. A row that's entirely negative numbers, our formula still works, because it's always comparing take this versus take that. So it correctly finds whichever path loses the least. If both players' best possible play lands them exactly even, DP0 naturally comes out to 0, and we correctly report a tie instead of guessing. And because we're using one backward loop with no recursion at all, 50,000 stones runs through this code just as safely and quickly as a row of 4. Let's tie it all together. We opened with a trap, clap 3 piles, bang 6 points, and Bob still wins with a leftover 7. Proof that taking more stones isn't the same as winning more points. That's exactly why we stopped tracking 2 separate scoreboards and started tracking one single number instead. The score gap between whoever's playing and their opponent. We fill that DP list backward. One slot per position, always trying all 3 choices of taking 1, 2 or 3 stones. And at the very end, we just check the sign of DP zeros. Positive, negative or 0. And that sign alone tells us the winner. If you followed the whole thing, you now understand score gap DP, and you'll spot this exact shape again in future problems. Want to go further? Stone Game 2 changes the rules. So the 1 to 3 limit adds